Hello and welcome to Aviation Republic. My name is Joe. This is the story of how a neutral nation gambled its defense on building one of the most advanced combat aircraft of the Cold War, designed not to win wars, but to turn Sweden into a 174,000 square mile hedgehog, far too dangerous for anyone to swallow easily. This part 1 is the development story, how Sweden went from a filing cabinet full of rejected designs to a flying prototype that the experts said couldn't exist. Part 2, coming soon, is what happened next, the testing that cost lives, the production crises, the 21 years of Cold War operations that proved whether the gamble paid off. This is Viggen. Arne Lacoma had been at this for 5 years, and he was running out of ideas. The Finnish-born designer led Saab's preliminary studies group, and since 1952 his team had produced more than 100 configurations trying to answer one question: what comes after Lansen and Draken? Every time they thought they'd cracked it, the requirements shifted. Interceptor in 1952, strike aircraft by 1954, multi-role by 1955. Each pivot meant starting over. Each layout that looked promising on paper ran into some wall. Too heavy, too expensive, too complicated for conscript maintenance crews. Then in April 1957, a British politician made everything worse. Duncan Sandys, the UK's Minister of Defence, published a white paper declaring manned combat aircraft obsolete. The British government would cancel most of its advanced manned combat aircraft projects, believing the future pointed towards missiles. The decision didn't stay in Britain. Across Europe, air staffs took notice. In Sweden, they called what happened next the British phobia. Flygstaben, the Swedish air staff, looked at this white paper from a major military power and thought, are we about to waste millions of kroner on a new manned fighter? If the British say aircraft are finished, maybe we should just build missiles. Work on future fighter projects stopped. The phobia was premature. In Britain, the P-1 that would become the Lightning was already flying, and they would eventually resume military aircraft development. But in 1957, nobody in Stockholm could know that they would. The Saab 35 Draken, still in development and not yet in squadron service, was now assumed to be the last manned fighter Sweden would ever build. That assumption erased Lacoma's 5 years of work in a stroke. But why did Sweden need to build a new fighter at all? Why not simply buy American starfighters off the shelf? The answer to that question lay in a word that sounded peaceful but wasn't: neutrality. Sweden had been neutral for nearly a century and a half. No wars since 1814. But neutral didn't mean safe. It meant you fought alone, and it meant your suppliers could vanish overnight. The Swedes had learned this the hard way. In 1939, the Air Force had ordered 300 combat aircraft from the United States, Seversky P-35s and Vanguards. Then Germany invaded Norway. Suddenly, Washington was worried that any weapons shipped to Stockholm might end up in Berlin. In 1940, America embargoed all military sales to neutrals. The aircraft Sweden had paid for never arrived. That lesson shaped everything that followed. In a European war, spare parts, ammunition, replacement aircraft, none of it was guaranteed. A neutral nation couldn't build its defense around equipment that might stop arriving the week the shooting started. So Sweden built its own, had done for years, and these weren't second-rate machines. In less than a decade after the war, Saab had produced Canard, Lansen and Draken. The question in 1957 wasn't whether to build, it was whether they could build something good enough to match what was parked on their borders, because its geography made that question urgent. Sweden sat between NATO and the Warsaw Pact, with a Baltic coastline that Soviet amphibious forces could cross in hours. Her land border stretched more than 1,000 miles of territory that both sides might want in a European war. And she sat astride the Soviet Baltic's fleet route to the Atlantic, a position that made her strategically valuable to everyone and allied to no one. Swedish defense doctrine didn't assume Sweden could win a war against the Soviet Union. It assumed Sweden could make the cost of invasion unacceptable. The strategy was called total defense. Every citizen had a wartime role, whether in uniform or not. During the Cold War, Sweden could mobilize hundreds of thousands of people within days. Critical infrastructure, roads, bridges, power stations was designed with precast demolition chambers, so an advanced enemy would find nothing useful left standing. Sweden built one of the largest networks of rock shelters, including hangars blasted into the bedrock where aircraft could disappear entirely. The country was literally wired to fight from the first hour. At the center of this doctrine was the Air Force. Swedish planners had run the numbers. Soviet Tu-16 bombers could reach Stockholm quickly enough that warning time was measured in minutes. The Soviet Baltic Fleet, supported by tactical air forces based in the Baltic states, East Germany and Poland, could launch coordinated amphibious and airborne assaults with minimal warning. The assumption wasn't weeks of build-up, it was hours. By the time diplomatic cables were flying, the first wave would already be airborne. In an attack, conventional air bases would be craters within the first hour, runways destroyed, hangars burning, aircraft caught on the ground. To be sure they wouldn't be caught off guard, Sweden's signals intelligence constantly monitored Soviet communications. If it detected the machinery of mobilization warming up, a warning would go out, and the entire air force would disperse into the forests before the first strike arrived. The concept was called BAS 60. Specialized highway sections hidden amongst the trees would serve as runways, with underground fuel tanks and ammunition bunkers built into the woods nearby, with a squad of teenage conscripts with a few months of training headed by an NCO servicing the aircraft. They would need to refuel and rearm the aircraft in 10 minutes flat and then send it back into the sky before anyone knew where to look. The forest wasn't a fallback, it was a shell game, and the prize was survival. Sweden was to become a hedgehog, too prickly to swallow, but surviving the first wave was only half the problem. A Soviet invasion meant amphibious landings, troop ships, landing craft, naval escorts crossing the Baltic. If those ships reached Swedish shores, no amount of dispersed fighters would matter. The war could be lost on the beaches. The weapon they'd use to sink the ships already existed, the RB-04. One of the world's first autonomous anti-ship missiles, and had been operational on land since the late 50s. Sweden didn't need a new way to kill ships. She needed an aircraft that could get in there fast enough, fly low enough, and survive long enough to use it. And that aircraft had to operate from highway strips no longer than 500 meters, carrying a full weapons load in any weather without ground radar support. That number, 500 meters, came directly from operational analysis of Swedish roads. The Air Material Board had been surveying the highway network since 1949, looking for sections that could be reinforced to take the weight of a loaded fighter, concealed from aerial reconnaissance and supported by turnaround sites hidden in adjacent forests. What they found were strips rarely longer than 800 meters, the length Draken needed, and as narrow as 9 meters. But 800 meters assumed everything worked. Drag chute deployed, brakes functioning, no ice, no battle damage, but Sweden wanted margin. Any new aircraft had to stop in 500 meters as a matter of routine, not as a best case scenario. If it couldn't, the dispersal doctrine was only as good as the weather. For comparison, the F-4 Phantom typically needed around 1500 meters of runway. A Mirage 3 required roughly the same. Sweden was asking for a supersonic strike aircraft that could operate routinely from 500 meters, less than a third of that distance, fully loaded in any weather. The Saab 32 Lansen could strike targets, but it needed long runways, the kind that would be rubble within the first hour. Draken was better. Her double delta wing let pilots land at extreme nose-high attitudes, 12 to 15 degrees, using the airframe itself as an aerodynamic brake. Combined with a drag chute, test pilots had put Draken down in as little as 450 meters. But there's a gap between what test pilots could achieve and what squadron pilots could do reliably, sortie after sortie, in winter conditions with battle damage on icy roads lined with pine trees. Draken proved the concept. Now Sweden needed an aircraft that could go further. The obvious answer was build a new strike aircraft, a Lansen replacement that could operate from highway strips. Let Draken handle the bombers and let the new aircraft handle the ships. But intercepting bombers wasn't the problem. Not yet. Draken could handle that for now. But aircraft don't last forever. By the time a new strike aircraft entered service, Draken would be halfway through her own lifespan. Eventually, Sweden would need to replace both, and she couldn't afford to do it twice. 2 separate programs, 2 production lines, 2 training pipelines, 2 sets of spare parts. For a nation of 8 million people with a tightening defense budget, that was a non-starter. What they needed was one aircraft that could do everything, a Swedish Army knife. For Lacoma, that meant reconciling requirements that had defeated every configuration he'd drawn for 5 years. But there was another path being investigated, one that might have made the whole fighter question irrelevant. While Lacoma's team ground through fighter concepts, he was leading a second program, one so secret that almost nobody at Saab knew it existed. A nuclear bomber designated Type A-36. Sweden's defense research establishment had been working on nuclear weapons since the late 1940s, and by the mid-50s they were collaborating with Saab on a bomb weighing between 600 and 800 kilograms. The idea was the A-36 would fly it across the Baltic at extreme low level, supersonic, and drop it on a Soviet naval base, destroying the invasion fleet before it ever sailed. Project 1376 came closest to something buildable, single seat, single engine, designed for supersonic low-level penetration across the Baltic. The missile advocates reckoned they had a better answer. In September 1957, Saab began work on Robot 330, a nuclear-armed cruise missile. Engineers built a transistorized digital computer for its guidance system, one of the most advanced Sweden had produced. But a cruise missile is a one-way decision. Once launched, it can't be recalled. It can't loiter over a border during a tense standoff. And it can't identify an unknown contact and decide not to fire. For a neutral country trying to manage crises without stumbling into escalation, this option was unacceptable. Sweden needed weapons that could threaten without committing, that could be seen without being used, and not accidentally start in World War III. Sweden also couldn't justify an aircraft that could only carry a nuclear weapon. The A-36 would be ruinously expensive for a single mission type, and could be useless the moment the nuclear program stalled. By 1958, both nuclear paths were dead ends. Type A-36 was cancelled, and Robot 330 died alongside it. With those paths closed, the air staff shifted focus. The irony was almost perfect. The British phobia had pushed Sweden towards missiles. The failure of the missile path pushed them back towards manned aircraft. But the debate had consumed nearly a year. And while the nuclear bomber and missile programs had been running into walls of their own, the air staff had already started asking a different question. Not whether to build a new fighter, but whether Sweden still could. In December 1957, Saab sat down with the Swedish air staff to work out what the Air Force actually needed. Not what they'd been assuming or what the missile advocates wanted, but what a manned aircraft would have to do if they were going to build one at all. That meeting changed everything that followed. What came out wasn't a wish list, it was a constrained set that assumed the worst. Main bases destroyed in the first hour, no ground radar, no factory support, and no retreat to better conditions. If Sweden built a manned aircraft, it would have to survive that scenario, or it wouldn't be worth building. The specification, once written, would be locked, or nearly so. Planners understood that a flexible system required gradual adjustments rather than unnecessary rigidity, but the core requirements were firm. What came from the air staff was a requirement for an aircraft that could intercept bombers at Mach 2 and strike invasion fleets at Mach 1, down at ground level where radar couldn't find it. It also had to carry the RB-04 anti-ship missile and engage targets in any weather. It had to land and take off in 500 meters on those reinforced highway strips, carrying a full weapons load, and be turned around in 10 minutes by a team of 1 technician and 5 or 6 conscripts working from a forest clearing. 1 pilot, no navigator. 1 airframe had to do it all, what they called a unit aircraft. Not 1 machine switching roles, but a family of variants sharing enough DNA that Sweden could build, train and maintain 1 fleet instead of 4. Sweden needed one aircraft that could do everything: sink ships, intercept bombers, fly reconnaissance missions, perform ground attack, while surviving the hours and days after a Soviet invasion. Nobody had built anything like it. Most experts said nobody could. A month later, Saab opened 2 new lines of study, another attempt to stretch Draken as the conservative option and an entirely new aircraft as the ambitious one. Lacoma's team had already looked at the shortcuts. The 1400 series studies from 1956 to 57 had examined stall and vertical takeoff concepts, tail sitters like the American Ryan X-13, jet deflection schemes with afterburning flaps, lightweight deltas designed as cheap stopgaps. None of them worked. Most were either too expensive or too complex, far beyond anything Sweden could maintain with their conscript ground crews. Draken couldn't be stretched far enough. Her double delta was designed to go fast at altitude, not haul bombs off a frozen road. She was simply the wrong shape. By 1958, Lacoma's team had hundreds of rejected designs behind them and no way to simplify their requirements. Sweden's options were starting to look bleak. Buy foreign and risk embargo. Build cruise missiles and risk escalation. Stretch Draken and fall short. Every door had closed except one. Buried amongst those failures was a configuration Lacoma had set aside 3 years earlier. Project 1357. The aerodynamicists said it was unstable. The wind tunnel data was inconclusive. But the filing cabinet was full and the specification wasn't going to change. And if Sweden was going to become a hedgehog, that would be a door they'd have to open. If you're enjoying this story, please take a quick second to hit the like button. It's a small gesture that makes a huge difference in helping me reach more aviation fans. Now, let's get back to the story. Eric Bratt had led the team that designed Draken. That probably made him one of the only aircraft designers in Sweden who could look at the specification document on his desk and not immediately dismiss it as fantasy. The thing read less like an aircraft requirement and more like a list of reasons why the machine couldn't exist. By 1958, Bratt was heading up the renewed effort. Years of work under Arne Lacoma had produced a filing cabinet full of configurations, each one defeated by requirements that kept shifting. Sweden's acquisition of American radar-guided missiles, the RB-27 and RB-28, had brought Draken a longer lifespan. The requirement though hadn't changed. Eventually one aircraft would need to do everything, but for now Sweden had breathing room. The attack variant would come first and the interceptor would follow. But every obvious path had been tried and none had worked. Bratt needed to find, as they had with Draken, a path that wasn't obvious. That search was already underway. The 1500 series of studies had begun after the December 1957 meeting, a systematic search for something that could meet the BAS-60 requirements. The problem was always the same: stall performance versus supersonic speed. Every configuration they looked at solved one problem only to make another worse. Draken had solved the stall issue with its double delta, a sharply swept inner section for high-speed performance and a more gently swept outer section for lower speeds. It was elegant and it worked. The obvious question was whether they could push it further. From the late 50s, Saab once again tried exactly that. They called it the 35 Olympus at first. The double delta scaled up by about 6%, fitted with a Bristol Olympus 22R, pushing out over 30,000 pounds of thrust with reheat. Along the way, the design picked up a kaleidoscope of names just to make things interesting, evolving to 35:37:AN, then to Super 35, and in 1960 became 37-1, after which the whole effort was redesignated Aircraft 37, not to be confused with System 37, the program that would eventually produce Viggen. Same number, different aircraft. Worth mentioning, 35:37:AN isn't a typo. Swedish puts the at the end of words. It's why Draken means the dragon and Viggen means the thunderbolt. The concept was straightforward enough. keep Draken's geometry, and add thrust reversing to the engine to shorten the landing roll. Flaps or clamshell doors would swing over the jet nozzle and deflect the exhaust forward, the same principle Panavia used on the Tornado. The thrust-to-weight ratio looked promising, and since the geometry was familiar, this meant lower development risk. But it wasn't enough. When Saab ran the numbers for 500-meter landings with full weapons load, the double delta couldn't generate the lift. By late 1961, they'd closed that line of research, and the safe option was gone. Whatever came next would be a gamble. If Saab was going to meet the requirements, it would need something other than a bigger Draken. Variable geometry, swing wings, was fashionable at the time. The Americans were pouring research money into the concept at NASA. Barnes-Wallis had also been working on variable geometry at Vickers, but his Swallow design, a supersonic V-bomber replacement with swing wings, was cancelled in 1957. The idea was seductive: sweep back for speed, sweep forward for slow flight. One aircraft, two configurations, best of both worlds. So the Saab engineers ran the analysis, and it wasn't long before they hit problems. The variable geometry mechanism added weight. The structural reinforcement added more weight. The complexity added development time the program simply couldn't afford. And there was another problem nobody talked about much in the technical literature. A swing wing mechanism needs maintenance. Careful maintenance. The kind of maintenance that assumes hangars, train technicians, and hours between sorties, not forest clearings, conscripts, and 10-minute turnarounds. BAS 60 didn't allow for complexity that couldn't be inspected by torchlight in the middle of winter. Internal assessments used the terms mass disadvantageous, which was the polite versions. So swing wings were out. Project 1508, presented in March 1961, went back to a design configuration Lacoma had already tried: lift engines. This configuration looks surprisingly modern: pure delta wing, clean lines, something like a Dassault Mirage 2000 20 years early. One Rolls-Royce Spey for cruise power, two lift jets buried in a fuselage that would fire up during takeoff and landing, although some sources state that the lift engines were in the nose, which I thought was strange. Maybe it was ducked into the nose. If you know, comment below. The idea was clever. A pure delta needs a high angle of attack to generate enough lift at low speeds, and the nose pointed so high the pilot can barely see the runway. The lift engines would trim away at the nose-high altitude, letting the aircraft approach flatter, slower, and stop shorter. The trouble was ground effect. When the lift engines fired close to the ground, their downwash interfered with the wings in ways the control systems of the era couldn't reliably compensate for. Pilots would have been fighting unpredictable pitch changes all the way to landing. Saab's engineers tried to solve it with Project 1511 that pushed the concept further. Instead of 2 lift engines, it would have 4. But predictably, it made the ground effect problem worse, not better. Lift engines are interesting in principle until you realise they're dead weight the moment you're airborne, not to mention the fuel consumption was punishing. For an aircraft that needed to fly combat missions from highway strips with turnaround times counted in minutes, hauling around engines that served no purpose after takeoff was an absurdity Saab couldn't afford. Both the lift engine ideas were dropped, and into the filing cabinets they went. However, a refined variant, the 1508A2, would resurface later as a finalist, but the fundamental problem remained. To Eric Bratt and his team, it was the same Draken problem repeating itself. High speed versus low speed. Every solution they tried solved one at the expense of the other. The double delta couldn't generate enough lift for 500-meter landing runs. Swing wings were too heavy, too complex, and too slow to develop. Lift engines couldn't be made to work. By 1959, they'd eliminated almost everything. But one configuration remained that hadn't been properly analysed. Not because anyone trusted it, but because no one had wanted to spend the wind tunnel time. Thorson Ornberg had been running tests anyway. Working in Saab's aerodynamics group, he'd spent much of the previous year experimenting with Canard delta combinations. His colleagues weren't sure what to make of the results. The numbers looked too good. Ornberg's wind tunnel model suggested the configuration could deliver dramatically more lift than a conventional delta, perhaps as much as 50% at high angles of attack. But he wasn't working alone. Herman Berbohm and Bertil Dillner were investigating the same configuration, building a theoretical case for what Ornberg was measuring empirically. Canards weren't new. The Wright Flyer had a Canard. But there's a difference between a fabric-covered wooden biplane wobbling through the air at Kitty Hawk and a production fighter pulling combat maneuvers at twice the speed of sound. The term that mattered was close coupled. The Canard had to sit near enough to the main wing that the vortices they generated would still be spinning when they reached the delta's leading edge. Position it too far forward and they'd dissipate before they arrived. Weight and drag, but no lift bonus. The XB-70 Valkyrie had 4 planes set meters ahead of the delta, but those were for trim, not lift. Saab needed something different. At low speeds, a close-coupled Canard would generate additional lift. At high angles of attack, something stranger would happen. Those vortices rolled back over the main delta, energizing the airflow and keeping it attached at angles where a conventional delta would stall. The Canard would be fixed, not a pilot-controlled surface like on later fighters such as Gripen or the Eurofighter. The pilot had no input to the 4 planes whatsoever. Only a trailing edge flap moved, linked mechanically to the landing gear. Wheels down, flap down, no electronics, no software. Nothing that could fail when the aircraft was sat in a forest clearing with a 19-year-old conscript turning the wrench in -20. Pitch control came entirely from elevons on the main delta's trailing edge. Also, it wasn't a case of simply bolting a pair of scaled-down deltas to the nose and calling it a day. If the Canard sat too low, its weight would blanket the main wing, killing lift exactly when you needed it most. Too high and the vortex interaction weakened. The solution? Mount the 4 planes slightly above the main wing's plane, fixed at a steeper angle. During the approach, the Canard would hit its lift limit first. When a wing reaches that limit, it stalls. If the geometry was right, the Canard would stall gently, dropping the nose rather than pitching it up. Whether it would survive contact with real air was another question. BAS 60 didn't assume pilots would be fresh and rested. It assumed they'd be flying their 3rd sortie of the day, landing on unfamiliar highway strips, possibly with battle damage, definitely without ground control that made precision approaches routine. An aircraft that warned you gently before it bit was an aircraft that might bring you home. In October 1959, Brad put a small team on a subscale Canard project. Saab 211, presented later that month as the 37 Junior. The idea was to do what the Saab 210 had done for Draken a decade earlier, prove the configuration before anyone risked a full-sized aircraft. It was never built. The program couldn't afford the time or the money. This time the Canard would have to prove itself at full scale or not at all. Saab was running multiple studies simultaneously throughout 1961. While Ornberg, Berbohm and Dillner refined the Canard Delta, Saab's design office was working through a parallel competition. These were systematic evaluations of wing shapes and engine integrations. By late 1961, the field had narrowed to 2 finalists. Project 1562, a highly swept tailless delta powered by the Bristol Olympus with jet deflectors. This was Eric Bratt's main alternative. Then there was Project 1508A2, a refined lift engine concept, still spay-powered with 2 lift jets. Neither finalist was a Canard. The wind tunnel work on the Canard Delta wasn't finished. The configuration still carried too many unanswered questions about pitch stability to put in front of the air staff alongside designs that had full performance data and brochures ready to go. Then, on the 21st of November 1961, Berbohm and Dillner walked into a meeting with data that upended everything. Their wind tunnel results answered the question that had haunted the Canard since 1954. Experts had been worried that the main delta might stall first, pitching the nose up violently, a departure at low altitude that no pilot could recover from. Boehm and Dillner's data showed the opposite. The Canard would stall first and gently. As lift faded on the foreplane, the nose would slowly drop, the angle of attack would reduce, and the aircraft would correct itself. It would warn the pilot before it killed him. It seems that the Canard was indeed flyable. Saab's technical director Lars Brissing, on seeing the data, now insisted Canard alternatives be added to the evaluation. Within a week, Saab produced drawings of two Canard configurations, Project 1504 powered by the Rolls-Royce Spey and Project 1564 powered by the Bristol Olympus. The Canard was now firmly in the race. Then, 2 weeks later, everything changed again. In early December 1961, the KFF, the Royal Swedish Air Force Material Administration, announced that they had found a new engine option, the American Pratt & Whitney JT8D. The announcement blindsided Saab. KFF had been negotiating with the American engine manufacturer without telling the design teams. The JT8D had never appeared in any engine study, not once. By the time the engineers learnt of it, the KFF had already decided. What was interesting about this engine was that it was a civilian turbofan, not a military engine, and it was already flying on airliners. More importantly, it was one that didn't depend on British defence programmes for its survival. That same day, Arne Lacoma sketched two new configurations for the JT8D. One was a conventional delta with jet deflection, the other was the Canard layout, now designated Project 1534. The JT8D was larger than the Spey, a fatter engine that needed a fatter fuselage. But it also had thrust margins that made something else possible, an integrated thrust reverser. No separate lift engines, no complex jet deflection, just clamshell doors behind the nozzle redirecting the thrust forward. The 500-meter problem now had an answer that didn't require complex machinery that would be prone to failure. The next day, the 9th of December 1961, KFF made its decision. Project 1534 would be the formal baseline for System 37. The months of work and all the other designs became obsolete overnight. Project 1534 took the Canard Delta geometry that Boehm, Dillner and Ornberg had validated in the wind tunnel and paired it with an American engine nobody had been considering a month earlier. By the time the proposal reached KFF, Lacoma was moving to head Saab's research and development division away from day-to-day design work. The aircraft he'd spent years trying to define would be built by somebody else's team. Saab submitted the formal System 37 proposal in February 1962. 9 years of studies, hundreds of rejected configurations and shifting requirements, and the defining choice came down to 3 weeks in November and December, distilled into a single aircraft, Canard Delta, single engine, thrust reverser for short-field operations. KFF reviewed the proposal through the spring and summer, and the official go-ahead came on the 28th of September 1962. The Canard geometry looked good on paper. The wind tunnel data was encouraging, but the gap between encouraging and proven had ended plenty of aircraft programs before. Some government aerodynamicists still maintain that an aircraft with these requirements couldn't be built, not a Mach II, not with a Canard. Saab's own engineers weren't entirely sure they were wrong. By year's end, 1,400 employees would be assigned to the project, billions of kroner committed. The question wasn't now whether it could meet the specification, it was whether anyone could fly it and survive. The shape was supposed to be frozen. The weight had other ideas. At program go-ahead, engineers had estimated takeoff weight at 11,870 kilograms. By October 1962, the first detailed specification, Type Configuration 1 or TK1, put the weight at 12,645 kilograms. TK1 was designed as a tandem two-seater, though in reality that space was really earmarked for fuel. The aircraft had oblique shock intakes designed for high speed efficiency, a mid-wing layout and landing gear housed entirely in the fuselage. An oblique shock intake uses a center body or wedge to create shockwaves that slow incoming air in stages, far more efficient above Mach 1.6 than a simple inlet. But the mechanism needs moving parts to adjust for different speeds, which means more weight, more complexity and maintenance, which was a problem. By February 1963, TK2 came in at 13,638 kilograms, 1,000 kilograms over the original estimate. The weight kept on climbing, something had to give. The solution was brutal, cut just under a meter from the fuselage. Any ideas of a second seat were gone and the undercarriage moved from the fuselage to the wings, which saved around 500 kilograms but forced a complete structural redesign. The intakes changed too. The oblique shock design was dropped in favour of simpler fixed geometry inlets, less efficient at high Mach numbers but lighter and easier to maintain. No moving parts, nothing to adjust. The aircraft would be slightly slower at the top end, but it would actually work when it mattered. This was also to be the first Saab aircraft to have the area rule formally applied during design. Area rule is a fairly simple idea discovered in the 1950s. As an aircraft approaches the speed of sound, drag doesn't just increase, it spikes violently. Shockwaves begin to form and the air resists being pushed aside. Engineers discovered something counterintuitive. It wasn't the shape of the wings alone that caused the problem, it was the total cross-section of the entire aircraft at every point along its length. Imagine slicing the aircraft into thin vertical sections from nose to tail. If you stack those slices into a graph, the curve should rise and fall smoothly. If the wings suddenly add too much area at one point, the fuselage must narrow there to compensate. If the engine makes the rear too fat, something forward must slim down. The goal is a smooth wasp waist profile, so the air isn't shocked by sudden changes in volume. Near Mach 1, smooth volume equals less wave drag. Less wave drag means more speed for the same thrust. With the large diameter engine taking up the rear fuselage, engineers had to waist the structure around it, narrowing the body where the wing joined. The result was expensive, structurally complicated, and as one engineer put it, pretty chubby. I'm not saying Viggen wasn't elegant, just robust. Her form was a geometric and aerodynamic necessity. The wing geometry was equally constrained. The numbers were specific. 6.2 square meters of Canard surface swept at 60 degrees, positioned to interact with 46 square meters of main delta. The wing itself had a compound sweep, 45 degrees near the fuselage, increasing to 57 degrees at mid-span. The compound sweep wasn't aesthetic. Wind tunnel testing had shown that heavy external stores disturbed the natural vortex flow over the wing. The natural sweep of the outer section was meant to keep the entire center of pressure stable across a wider range of angles of attack. As testing continued through 1963, two distinct issues surfaced, each needing its own solution. The first was structural. The thin delta wing was proven to be too flexible. Under certain conditions, when the pilot applied rudder, the wing twisted so severely that control effect reverse. Push right rudder, the wing deforms and the aircraft yaws left. Engineers called it the reverse rudder effect, a nightmare where the controls worked backwards. At high speeds, the thin delta would have deflected under pressure, and that deflection would have reversed the aerodynamic forces the inputs were supposed to create. The fix was brute force, strengthen the wing. Metal thickness in the main spar went from 12mm to 41. And, of course, the redesign added more weight. The shortened fuselage, the wing-mounted undercarriage from TK2 had saved 500 kilograms, but it wasn't enough. By early 1966, takeoff weight had climbed to 14,800 kilograms, nearly 3,000 kilograms above the 1962 estimate. That kicked off what Saab called a frantic wait hunt that lasted years. The specification needed the aircraft to fit inside existing rock shelters that had been blasted into Swedish bedrock for earlier smaller aircraft. Maximum height 4.5 meters. Viggen's fin pushed the aircraft to nearly 6 meters, nearly 1.5 meters above the limit. So engineers designed an automatic hydraulic mechanism that could fold the fin in under 30 seconds, fast enough that ground crews wouldn't be left exposed. It worked, but it was also heavy and complicated. Before the first prototype flew, someone asked whether 30 seconds really mattered. 3 minutes would be acceptable. That single question killed the hydraulics. Now he had a mechanic standing on the wing, cranking the fin down by hand. This could meet the relaxed requirement. Folded height, just 4 meters. Weight saved, at least 15 kilograms. Cost saved, considerably more. Every gram mattered now. The next problem was aerodynamic. Wind tunnel data showed the configuration hunting in sideslip, refusing to settle. The aircraft's nose wandered rather than tracking straight. The engineer's first instinct was to angle the canards upwards, adding 10 degrees of dihedral to the foreplanes. The V-shape was meant to stabilize the nose in sideslip. It was a fix, not a permanent solution. As development continued into the 60s, some engineers pushed for blown flaps. Compressed air bled from the engine to keep the boundary layer attached during high angle of attack approaches. In maintenance terms, it would have been a nightmare. High pressure ducting running through the airframe, seals that would degrade, bleed air that robbed engine performance exactly the moment the pilot needed thrust for a go-around. And for an aircraft designed to operate with conscript ground crews, complexity was the enemy. Saab rejected the whole approach. They'd rely on passive aerodynamics instead, the Canard delta configuration doing the work through geometry, not plumbing. The clever solution that needs perfect maintenance is worse than the crude one that works when it's cold and the mechanic is in a hurry. And weeks before the aircraft was scheduled to fly, verification testing proved that it behaved correctly, and in some respects better with the V-shape removed. Other than the Canard, Viggen's most distinctive feature is its truck-like undercarriage that looks like it has no business on a combat aircraft, and it's designed like this for good reason. Conventional fighters touch down gently, a flared approach, the nose easing up, and the main gear wheels kissing the runway. Viggen couldn't afford that. A flared landing needed runway length. Instead, Saab designed for what engineers called a smackdown. The aircraft arriving nose high at 135 miles an hour, then dropping onto the main gear at sync rates of 16 feet per second. Carrier aircraft landed like that. No other land-based fighter did. The gear had to absorb the impact and fit inside the wing too thin for conventional struts. Saab's solution was a tandem wheel arrangement, twin wheels on each main leg, one behind the other, that could distribute the landing loads while still retracting into the narrow delta. Smaller changes followed. The double curved windshield became a single-piece cylindrical front glass, better optics for the head-up display. Engineers tested rain runoff by mounting a Mach Viggen windscreen on a Draken and flying it through storms. It worked. Problems would emerge during flight testing that required a distinctive bump on the dorsal spine, but that story belongs to part 2. In April 1965, the layout was frozen. Type Configuration 3 or TK3, the baseline for the first prototype. 4 years of wind tunnel testing, hundreds of design iterations, and endless arguments over what the data actually meant, distilled into a single shape. Heavier than planned, more complex than intended, and still unproven in the air. The aerodynamic gamble had been refined as far as theory could take it. But an aircraft is more than just its aerodynamics. A single pilot was supposed to do the work of two: fly at treetop level, navigate without ground radar, find the target, release the weapons, and get home. Lanson had needed a navigator exactly for this reason. Viggen wouldn't have one. Instead, it would have one of the most sophisticated computers in the world. Bengt Everts and Bengt Sjöberg had been given an impossible job: to replace a trained human with transistors, ferrite memory, and a few thousand integrated circuits. Leading the hardware and software teams within Saab's systems department, a group that would become Data Saab, they were attempting something that barely existed anywhere in aviation: an airborne digital computer that could do a navigator's work. To understand why Saab needed the computer, you had to understand what it was replacing. A Lancer's navigator sat in a cockpit behind the pilot, surrounded by tools that would have been familiar to a bomber crewman in 1945. A radar display, a plotting board, a stopwatch, along with tables of numbers for calculating wind drift, ground speed and release geometry. Flying toward a Soviet convoy at 200 feet above the Baltic, his job was to watch the radar, identify ships, hand plot their positions on a paper chart, calculate attack geometry, and tell the pilot when to release. All while the aircraft bucked through turbulence over 500 knots, the radar display flickering with sea return, the cockpit shaking too hard to write clearly. If he got the sums wrong, they missed. If he got them badly wrong, they flew into the sea. The A-32 Lancer carried 2 crew for exactly this reason. No single human could fly the aircraft, navigate and manage weapons simultaneously. The workload demanded division. But Lancers didn't fly alone, they attacked in divisions, typically 4 aircraft, with the lead carrying a fully equipped and trained navigator who coordinated the strike for the entire formation. The problem was not every Lancer had a navigator and not every Lancer had radar. Only certain aircraft, the group leaders, sometimes the element leaders, were equipped and crewed to lead. The wingmen followed. If a Saab or Mach took down the leader in the first minutes of the engagement, the rest of the division lost their coordinator. They could still fly, they could still drop ordnance, but as individuals, not a coordinated strike. The solution here wasn't to add more navigators, it was to remove the single point of failure entirely, give every aircraft the same capability, so losing the leader didn't blind the formation. System 37 was supposed to do everything Lancer did at twice the speed with half the crew. The navigator's seat was gone. The scramble requirement made that position impossible anyway. Swedish doctrine assumed minimal warning. Soviet aircraft could cross the Baltic in minutes. Viggen had to be airborne in under 30 seconds from the alert, full combat systems active. If pre-connected to ground power, the aircraft could go from cold cockpit to taxiing in 60 seconds, navigation aligned, weapons computer ready. The navigator wasn't replaced because a computer could do his job. He was replaced because no human could do it fast enough. The computer wasn't about intelligence, it was about time, and his entire skill set had to go somewhere. Everts and Sjöberg's job was to make it fit inside a box the size of a filing cabinet. The proof that it could be done sat on a table in Linköping. The year before, a team at Saab had completed the D2, a transistorized prototype weighing 200 kilograms, built from 5,000 transistors and 25,000 other components. It could execute 100,000 instructions per second, and it had run sighting and navigation programs that proved digital logic could do a navigator's job. Now Everts, Sjöberg and their team had to make it fly. As with the aircraft, they were also building for a specification that kept expanding, because every time the aircraft designers added a new weapon or a new mission requirement, the computer had to absorb it. Not everyone at Saab thought what they were attempting was wise. Some managers viewed the computer as a danger to the System 37 program, an unnecessary complication that would delay production and inflate costs. The skepticism wasn't irrational. Airborne computers in 1962 were exotic, unreliable and expensive. The Americans had put digital systems in the F-106 Delta Dart, but those were interceptors with simpler mission profiles: climb, find a target, shoot and go home. But replacing a human navigator on low-level attack missions, now that was something else entirely. Most engineers didn't really know what it would mean in practice, but one test pilot later admitted, "I had great confidence in Bengt Sjöberg and his colleagues at Saab's systems department and was sure it would be fine." The confidence was justified, but only flight would prove it. In the early 1960s, Fairchild Semiconductor began demonstrating a new invention in Europe, the integrated circuit, multiple transistors etched onto a single piece of silicon. Until then, computers were built from thousands of discrete components, each mounted and soldered onto circuit boards. More components meant more weight, more heat, and more points of failure. An integrated circuit replaced clusters of individual transistors with a single chip, smaller, lighter, and dramatically more reliable. The phone in your pocket contains between 6 and 10 billion transistors. Built the old way, it would cover a football pitch. Saab sent engineers to investigate, and they liked what they saw. In those early days, before production lines were established, Swedish engineers travelled to California and, as one account put it, hung on the doors of Fairchild's laboratories to collect integrated circuits directly. Later, once the deal was signed and production scaled up, chips began shipping to Sweden regularly. Bjorn Holberg at Saab's Systems Department became the first person in Europe to hold one in his hand. Tiny brass capsules the size of thimbles, each containing a silicon chip 2 mm square. For a time, Saab was Fairchild's largest customer in the world. The chips gave them processing power. But a computer also needs memory, and so began the memory wars. Project management wanted a computer's memory limited at 2048 words of core memory, with each word having 28 bits, with 2 bits for parity meant the capacity would be just over 6 kilobytes of usable memory, or 7 kilobytes if you include the parity bits. Why am I such a nerd? For comparison, so you have an idea what they were working with, that's smaller than a basic text file today, and expensive enough that every additional word had to be justified. The engineers in Evertz's hardware team listened to this limit and understood immediately that it couldn't work. Navigation alone required algorithms for dead reckoning, Doppler velocity measurement, radio and beacon fixes. Weapons delivery needed ballistic tables for every weapon type, and Viggen was designed to carry rockets, bombs, guided missiles, and eventually cannon. Each weapon had different flight characteristics, different release parameters. The tables alone would swallow the memory budget before you got to the display formatting or fuel management. One engineer later described the management position as avarice cruelly deceived by wisdom. To make 2,000 odd words function at all, you'd have to use coding tricks and compressions that would cripple future modifications. One major compromise was forced early: the rejection of a true inertial navigation system. A proper inertial platform could give position without external references, no radio beacons to jam, no radar emissions to betray you. But the software wouldn't fit. They'd have to find another way. By 1969, reality had won. The memory stabilized at 8,192 words, 4 times what management had originally authorized. The ferrite core memory was a marvel of patience as much as engineering. Picture a tiny iron ring about 1 mm across, smaller than a grain of rice. A brief electrical pulse flips the ring's magnetic state one way or the other. One direction means 1 and the other means 0. That's 1 bit of memory being held. Now picture 8,192 words of 28 bits each. That's 229,376 tiny iron rings, each one needing to hold 4 hair-thin wires threaded through its center. The wires had to pass through in a precise pattern. Each wire handled different functions. Thread them wrong and the memory failed. Thread them right and it survived power cuts, vibrations and temperatures from -40 to +70 Celsius. The ferrite cores had another property that nobody expected to matter. They held their data without power. Loss of generator, combat damage, electrical fault, special circuits detected a drop and halted the memory mid-cycle, preserving whatever was stored. When the power returned, the computer resumed exactly where it left off. Unlike the semiconductor memories that would replace them, the ferrite cores stayed magnetized indefinitely. The ones and zeros remained in place, waiting to be read. Years later, when Viggen started being lost under mysterious circumstances, that property proved critical. Engineers would recover memory units from wreckage scattered across Swedish forests and Baltic shallows, read out the final seconds of flight data, and discover what was killing their pilots. But that's a story for part 2. The ferrite cores themselves came from Plessey in England, over 200,000 tiny rings per computer shipped to Sweden for assembly. The threading was done by hand, no machine could do it at the required precision. Workers sat at benches guiding tiny copper wires barely thicker than a human hair through rings smaller than peppercorns, building up the memory plane one core at a time. A single memory stack took weeks to assemble. A mistake meant starting over, and threading was only half the problem. The CK37 contained roughly 2,700 of these integrated circuits, plus 1,400 transistors, 650 diodes, 3,800 resistors, 750 capacitors, and 51,000 solder joints holding it all together. Every one of those joints was a potential point of failure. Saab's reliability model showed that solder joints would account for nearly half of all predicted failures. A cold joint, a connection that looked solid but had microscopic voids inside, could work perfectly on the ground and crack under vibration at altitude. The computer would fail. So Saab created a cadre of specially licensed solderers. They were trained and certified specifically for flight-critical electronics. Every joint was inspected under a microscope before the computer left the factory. To meet its flight reliability target, each individual component had to operate flawlessly for the statistical equivalent of several thousand years, not decades, millennia. By June 1966, Saab had accumulated 38 million component hours of reliability testing, over 4,000 years of cumulative operation, including 300,000 hours in actual flight conditions. In 1966, there was no textbook for digital flight reliability, so Saab wrote it themselves. The Americans had tried to help. Sweden's Defense Material Administration had ordered BIAX memory from Honeywell, believing it would be twice as fast, half the cost and half the size of the Swedish alternative. Engineers spent months at Honeywell's laboratories in Florida watching test after test fail. The outcome was the opposite of every promise. Half as fast, twice as expensive, twice as large. 8 prototypes, 8 million kroner, all of it wasted. When Honeywell received the cancellation, the hospitality vanished overnight. The Swedish engineers found themselves eating in the staff canteen, paying for their own meals. In all, the CK37 weighed just over 60 kilograms across 4 units and consumed roughly 600 watts. 8,000 28-bit words of memory and a processor capable of roughly 200,000 fixed-point instructions per second. The computer's write-protected memory held coordinates for every Swedish airfield and common waypoint, 6,656 words that couldn't be altered in flight. A failsafe to make sure that no software glitch could erase the map of Sweden. But the CK37, or Central Calculator as it would be called, didn't work alone. An Ericsson-designed radar system was being developed in parallel, but that integration would come later on prototype 37-3. For now, Jowitz's team had to prove the computer could do its job. The CK37's main calculation cycle ran about 10 times per second, meaning that every tenth of a second it recalculated position, prepared weapons solutions, updated displays, tracked fuels, and tested itself, while higher priority interrupts cut in whenever something urgent needed attention. That sounds slow by modern standards, but it was fast enough for navigation and weapons delivery in the 1960s. To give you some context, a modern processor is roughly 300 to 500 million times faster in terms of raw clock cycles than a CK37. The clever part was how it handled different speeds of information. Navigation data, position, heading, distance to waypoint could update 10 times a second and nobody would notice a lag. But a head-up display couldn't wait that long. If any symbols lag behind the aircraft's actual motion, the pilot might start to overcorrect, and during an approach at 50 meters altitude, chasing symbols is not where any pilot wants to be. So the engineers built a separate interrupt program that ran every 34 milliseconds, nearly 3 times faster than the main cycle. This handled the attitude data and display extrapolation, predicting where the aircraft would be a fraction of a second ahead and painting the symbols accordingly. So the main cycle ran the big calculations and the fast interrupt kept the symbol projection in real time. More or less. The pilot saw smooth responsive instruments. The computer was actually running 2 different clocks. Everts himself described the CK-37 as a spider in a web. Pilots would later call it the R2-D2 in the machine. It sat at the center of everything, translating between analog centers and digital displays, connecting the radar to the gyro platform to the head-up display. Nothing in the aircraft talked to anything else without passing through the computer first. If, though, the spider died, the web went dark instantly. But dark didn't mean dead. Although the CK-37 calculated everything, it controlled nothing. Every output went to a display: the HUD, the radar screen, the instrument panel. The computer couldn't actually move a control surface, couldn't adjust the throttle, couldn't override the pilot. If it failed, the pilot lost his navigation, his weapons delivery, lost everything that made Viggen more than a fast jet with bombs strapped underneath. So the aircraft kept flying and the pilot could still get home. And it was that architecture that was the break. Most fighters of the era had federated systems. Radar computed radar, weapons computed weapons, navigation computed navigation. Each box did its own job. They didn't talk to each other except through the pilot. The CK-37 centralized everything: one computer, one logic layer, every sensor, every display, every weapon passed through the same machine. The CK-37 would be upgraded continuously for 20 years after the first series delivery. 8,000 words became 12,000, then 20, and then 32,000. But the airframe stayed more or less the same. It was the capability that kept growing. For a neutral state expecting embargo in wartime, that mattered. No foreign alternative existed. Ulf Edlund, the former Saab designer and chairman of the Swedish Aviation Historical Society, later estimated that the CK-37 was 10 years ahead of anything else flying. The Panavia Tornado, which finally matched its capabilities, wouldn't enter service until 1981. A nation of 8 million people had built one of the most sophisticated flight computers on Earth. The CK-37 wasn't just capable, it was sovereign. Between 1970 and 1978, Saab delivered nearly 200 of them. The computers outlasted their predicted lifespan by a factor of 5, failing only once for every 6 times the engineers had calculated. Some were still flying upgraded but fundamentally unchanged into the 21st century. But before weapons, there was navigation, and navigation had a problem. Remember the compromise from the memory wars, the rejection of a true inertial platform? This is where it mattered. A proper inertial system, the kind the Americans fitted to their bombers, used precision gyroscopes, accelerometers to track every movement from a known starting point. Once aligned, it needed nothing from the outside world. No radio beacons for an enemy to jam, no radar emissions to betray your position. Viggen couldn't have one. One of the reasons was alignment time. A true inertial platform needed minutes to spin up its gyroscopes and lock onto the Earth's rotation. Swedish doctrine assumed those minutes didn't exist. Viggen had to be airborne in 30 seconds of an alert, navigation working, weapons ready. And the memory wars had killed it anyway. The software wouldn't fit. So Soberg's team had built something else, a pseudo-inertial system that fused data from half a dozen sensors, none accurate enough alone, but all useful in combination. The air data computer measured airspeed and altitude from pitot tubes and static ports, and the course gyro tracked heading. Rate gyros sense rotation, accelerometers caught every bump and turn. Together they fed a dead reckoning calculation that estimated position moment to moment. But dead reckoning drifts. Fly for 20 minutes on air data alone and you might be a kilometre off course. Fly for an hour and you could miss your target entirely. The solution was the Decker Doppler Type 72 radar, a downward-looking system that bounced signals off the ground and measured the aircraft's true velocity over the surface. Unlike air data, which measured speed through the air, the Doppler measured speed over the ground. Wind didn't fool it and drift didn't accumulate. The CK-37 combined these outputs using complementary filters, weighing each sensor according to its reliability. Trust the Doppler for steady-state navigation. Trust the gyros during hard maneuvers when the Doppler might lose track. Smooth the transition so the pilot never saw a jump. The mathematics were a forerunner to Kalman filtering, the technique that would later guide Apollo astronauts to the moon. Soberg's team developed their version independently, working from first principles. Weapons delivery was where the CK-37 would really have to justify its existence. For unguided rockets, the computer calculated the firing point by integrating radar distance to the target with wind and target velocity. It could solve the problem in seconds. For bombs, the CK-37 handled two modes. The first was called Continuously Calculated Impact Point, or CCIP. The computer projected where a bomb would hit if released at that instance, accounting for speed, altitude, dive angle, wind and weapons ballistics. That prediction appeared on the head-up display as a symbol overlaid over the real world. The pilot flew towards a target, watched the symbol drift across the ground and released when it crossed the aim point. The second mode went further. The pilot designated the target on radar, locking its coordinates. The CK-37 tracked the aircraft's position and calculated release geometry continuously. The pilot simply flew the approach. At the precise instance the geometry was right, the computer released the weapons automatically. The pilot's hands weren't even on the release. The machine decided. What Lanson's Navigator had done with stopwatch and tables would now happen faster than any human could match. But none of this mattered if the pilot couldn't see the data. The head-up display was the interface between the CK-37's calculations and the human who had to act upon them. It came from Svenska Radio AB, adapting British technology from Elliott and Smiths. The challenge was optical. Projecting symbols for a curved windshield created distortions that made the imagery drift relative to the real world. The solution was double reflex glass, which widened the field of view and stabilized the symbology against the horizon. At low level, cluttered symbols could obscure the terrain. The solution was simplicity, geometric shapes transparent enough that the pilot could see through them. The fart vector, Swedish for velocity vector, or what pilots today call the flight path marker, along with heading, waypoint indicator, altitude and weapon symbology, all of it had to overlay the real world without hiding it. The central symbol was the flight path marker, showing where the aircraft was going, not where it was pointing. In turbulence, in crosswinds, in any condition where heading and actual path diverged, the flight path marker always pointed in the direction of travel. Viggen's approach profile was unlike anything Swedish pilots had flown. No flare, fly at constant angle of attack, nose high, flight path marker pinned to the touchdown point. Let the aircraft settle onto the runway. All the pilot had to do was put the flight path marker where he wanted to land and trust that the symbol was telling the truth. The problem was that the symbol wasn't always correct. Early testing on Lanson testbeds showed the flight path marker was unstable. When the pilot lifted the nose, the symbol followed with a delay. When he stopped pulling, the symbol overshot, oscillating before settling. At high altitude, annoying. At 50 meters, lethal. Engineers working on the head-up display found the fix. They called it the attitude clutch. The problem was that the symbol watched the aircraft, not the pilot. It waited to see what the aircraft did, then moved to match, always a moment behind. The fix was straightforward. Connect the symbol to the stick instead. Move the stick, the symbol moves. Stop the stick, the symbol stops. No waiting, no overshoot. The fix also solved the second problem. In the original system, a gust that lifted the nose would kick the flight path marker upward. The pilot's instinct was to shove the nose down to correct, By then the gust had passed and now he was overcorrecting. Another gust, another correction, and suddenly the pilot was chasing the symbol up and down, oscillating towards the ground. The attitude clutch cancelled out the gust. The pilot would see stability even when the air was rough. In a simulator it worked, and in the Lantern testbed it also worked. And there was also another problem that nobody had anticipated. Evertz's team had designed the computer, Soberg's team had written the software, tested it in the lab, flown it in Lancers. But they had no system, none at all, for updating the software once the aircraft entered service. In the early 1960s, this hadn't occurred to anyone. Aircraft had hardware. Hardware was maintained by replacing broken parts. The concept of software needing patches, updates, modification for bugs discovered in the field, this was new territory. Writing code for the CK-37 was an exercise in patience. Engineers wrote their programs by hand, one instruction per line on coding sheets. When the sheets were ready, they went to the punch room. About 20 women worked there, seated at teletype machines, translating handwritten code onto paper tape. But Saab didn't have the computing power to assemble the code themselves, not yet, so the tapes travelled. An IBM 360/40 sat in a bank at Linköping. Running a small program took half a day. For bigger jobs, they used an IBM 360/70 in Stockholm. Runs performed overnight, results collected the next morning. The assembled machine code came back on massive rolls of paper tape, ready to be loaded into the CK-37. If there were errors, and there were always errors, the engineer marked the corrections in red pen on the printout and the tape went back for repunching. The cycle repeated until the code was clean. When bugs were found, corrections were punched onto new tapes and spliced onto the program, and the fixes naturally piled up. By the time an edition was ready for flight testing, engineers were shipping patchwork, the original code plus dozens of corrections stitched together in sequence. There was no way to tidy it up until the next major version. Early testing threw up bugs that ranged from subtle to catastrophic. The velocity vector program, the code that painted the flight path marker on the HUD, suddenly started oscillating. Every input produced wild swings. Dag Folkson, one of the original programs, traced it to a single missing line, a return instruction that told the computer to stop executing one subroutine before starting the next. Without it, the filter ran twice per cycle. The symbol couldn't hold still. When cannon testing began, pilots reported a gun sight going dark mid-flight. The CK-37 was flagging a fault in its own input-output system and shutting down the display. The cause was two instructions in the wrong order. Normally it didn't matter, the code worked either way. But program interrupts could fire at any microsecond. On that flight, in that program edition, an interrupt landed between two swap lines, the self-test failed, and the display went black. Murphy's Law written in assembly code. The worst bug appeared slowly. The optical sighting function degraded over several flights, accuracy dropping, shots going wide. Engineers burned through expensive test sorties trying to isolate the problem. Folkson's team found it by reading machine code line by line. It turns out that a recent patch had introduced a scaling error. Someone had shifted a value 2 binary places too far. The gun sight was calculating with numbers 4 times too large. Each bug taught the same lesson. Software didn't fail like hardware. Hardware broke suddenly, a cracked solder joint, a burnt component. Software failed in the gaps between intentions. The line you forgot to write, the order you didn't think mattered, the patch that fixed one thing and broke another. When bugs surfaced during production aircraft flights, Saab issued amendment strips, lengths of punch tape meant to be spliced into the master program. The trouble was that the squadrons couldn't use them. Some never received the strips, others couldn't read them. None had the equipment to generate a complete program from partial updates. The solution was configuration management, version control, naming conventions, a system for proving which code was in which aircraft. For production aircraft, Ericsson built a test vehicle that could drive up to a dispersal point, plug in and update the software. The entire Viggen fleet could in theory be updated overnight. Later, built-in test equipment on the JA-37, the bulky vehicles gave way to portable tape recorders that could be carried by hand. So Viggen didn't just pioneer integrated avionics, it also pioneered the wonderful bureaucracy we all love in configuration control management. So now the computer was ready, the engine was next. The facility at Trollhättan had been rebuilding foreign engines since 1930. Svenska Flygmotor, later Volvo Flygmotor, started with the Bristol Pegasus radial, built under license for Gloucester Gladiators. During the Second World War, when supply lines from belligerent nations dried up, Flygmotor engineers, reverse engineers Pratt & Whitney's twin Wasps recovered from downed aircraft. They called these Chinese copies and given a designation of STWC-3s. Those reverse engineers twin Wasps flew in Swedish bombers until the war ended and a proper licensing settlement could be arranged. The de Havilland Goblin came next, then the Ghost, followed by the Rolls-Royce Avon. Each engine arrived as a foreign design and left as something Swedish, modified, adapted, fitted with locally developed afterburners that became Flygmotor speciality. In November 1961, the KFF chose an engine that surprised nearly everyone at Flygmotor. The candidates had been studied for years. Bristol Siddeley's Olympus 22 was Saab's favourite. It had the thrust Viggen needed. Flygmotor had built Rolls-Royce Avon variants under license for a decade. The RM5 for Lanson, the RM6 for Draken, and that long relationship with British engine makers gave them confidence they could work with another British design. But KFF rejected it. The Olympus was tied to the British TSR-2 program, an aircraft that hadn't reached production and might never. British defence politics had nearly killed manned military aviation entirely 4 years earlier. Westminster wasn't a foundation on which to build Swedish national survival. The Rolls-Royce Medway carried similar risks. It needed RAF adaptation that never came. Pratt & Whitney's military J75 was proven. It powered the F-105s, the F-106s, but it was the wrong engine for the wrong mission. The J75 was a pure turbojet, built for high-altitude interception, heavy, thirsty, and a generation behind the turbofan designs in fuel economy. Viggen needed low fuel consumption for sustained low-level flight, not raw thruster altitude. Some at Saab preferred the TF-30, but Pratt & Whitney was busy developing it for the US Air Force and couldn't spare the manpower. What they could offer was a JT-8D, a civilian turbofan, not a military engine at all. The same power plant pushing Boeing 727s and DC-9 through the sky. No afterburner and no thrust reverser. Designed for reliability and gentle throttle movements, not combat at treetop level. Pratt & Whitney proposed that Volvo Flygmotor take the core and develop the military version for themselves. It was an odd solution, but Sweden needed an engine that existed now, and the JT-8D's operational record on airliners was the closest thing to a reliability guarantee that purpose-built military engines couldn't yet match. In May 1962, Svenska Flygmotor signed a licensing agreement with Pratt & Whitney. The access wasn't accidental. In 1960, under the Eisenhower administration, the United States and Sweden had established a secret military technology agreement, what became known as the 37 Annex. The arrangement gave Sweden access to advanced US aeronautical data, NASA research engine integration support, and foundational work on digital avionics. According to Swedish defense researchers, the American motivation was strategic. US Polaris submarines operated off the Swedish coast, and Washington wanted a capable Swedish Air Force to help protect them from Soviet anti-submarine aircraft. Sweden got their technology, America got the neutral buffer that served Western interests without requiring NATO membership. Saab engineers later estimated the arrangement let them skip 5 to 10 years of trial and error. The JT-8D license was possible because of it. But it also came with strings that could be pulled at any time. The following year, 3 crates arrived from Connecticut containing the American engines. Stig Laurel had joined the company in 1962 as a project engineer. In 1963, he was one of the men staring at the crates from Connecticut, working out what they'd actually been asked to do. The task wasn't modification, it was reconstruction. A civilian turbofan operates in a narrow envelope, subsonic speeds, moderate altitudes, predictable thrust demands. Viggen needed an engine that could survive sustained afterburner, tolerate violent airflow disturbances at supersonic speed, and accelerate from idle to maximum thrust in seconds. The military flight envelope meant higher pressures and temperatures throughout. By the time Flygmotor finished, almost none of the original JT8D's components survived unchanged. If anyone's watched the television program Only Fools and Horses, this was Trigger's broom. In principle, very few parts from the basic engine, such as pure standard items like bolts and nuts, could be used on the RM-8A. Laurel's team replaced materials with high-temperature alloys, and the dimensions grew. The shaft between the low-pressure turbine and compressor was redesigned, as were the bearing housing, gearbox and oil tank. Flygmotor built a 3-stage afterburner, an entirely new fuel system, and integrated a thrust reverser, one of the first on any Western afterburning turbofan. The afterburner wasn't a simple on-off switch, it had 3 separate zones, each with its own fuel injection and ignition. Zone 1 was the hold-in zone, lighted up and the engine produced enough thrust to maintain Mach 0.9 at a low altitude with a full weapons load. Enough for sustained combat maneuvering without draining the tanks dry. Zone 2 was for acceleration and takeoff. The additional fuel flow pushed thrust up sharply, getting the aircraft off the 500-meter strip with ordnance under the wings. Zone 3 was brute force, maximum reheat. The penalty was fuel consumption. At full afterburner, the RM-8 drank about 15 kilograms of fuel every second. Viggen's internal tanks held enough for 7 minutes at that rate. 7 minutes and the gauges hit empty. The original JT8D produced roughly 14,500 pounds of static thrust at sea level. The RM-8A with afterburner lit pushed around 26,000, nearly double the civilian original. The RM-8A was a turbofan, meaning some of the air went through the hot core while the rest bypassed around the outside, driven by the fan but never heated. The bypass ratio tells you the split. The RM-8A ran 1.07 to 1, meaning slightly more air went around the core than through it. That bypass air made the engine more fuel efficient at low level, which was the whole reason they'd chosen it, but it also made the engine physically wider. At 1.35 meters in diameter and 6.1 meters long, the RM-8 dwarfed most Western fighter engines. Only the Soviet Tamansky R-15 in the MiG-25 was larger among operational fighters of the era. For comparison, the General Electric J-79 that powered the F-4 Phantoms produced roughly 79 kilonewtons of thrust. The RM-8A pushed 115 kilonewtons with afterburner. The Swedes had taken a civilian turbofan and turned it into a monster. But that size came at a cost. The whole aircraft grew larger and heavier than originally planned. The engine's girth forced the main undercarriage out of the fuselage and into the wings, a change that complicated weapons pylons and created new problems with structural loads. Each fix added weight and weight added cost. The engine that was supposed to simplify the program had made everything else harder and more expensive. The thrust reverser was unlike anything on a Western fighter. 3 clamshell doors, massive titanium segments sat behind the exhaust nozzle. In normal flight, they formed part of the variable ejector nozzle. On landing, they became brakes. The sequence for this was automatic, but it all started with the pilot. On final approach, the pilot pulled a lever in the cockpit to pre-select reverse thrust. Nothing happened yet, the door stayed open and the engine ran normally. The The system was armed and waiting. The moment the nose wheel touched the runway, the oleo strut compressed under the weight of the aircraft. That compression tripped a mechanical limit switch, a simple pressure sensor that completed an electrical circuit. That circuit commanded the hydraulic actuators, and the 3 titanium doors slammed shut in less than a second. With the exhaust path blocked, the jet blast had nowhere to go but forward, out through 3 slots cut into the rear fuselage. The geometry angled the thrust downward as well as forward, which did 2 things. It pushed the aircraft firmly onto the runway, improving braking traction, and it kept the hot exhaust from curling back around and being ingested into the engine intakes. Those 3 slots also mixed ambient air with the exhaust, cooling it before it hit the airframe. The pilot would, on landing, shove the throttle forward, full power, but now with all the thrust pushing the other way. The system generated roughly 7,700 pounds of braking thrust. Combined with the wheel brakes, Viggen could stop in distances that looked unnatural for an aircraft that weighed over 14 tons. The whole sequence touched down 2 full reverse thrust to seconds.
És nagyon rövid szakaszokon kitelepülnek tábori körülmények között a vadász pilóták, illetve műszaki állomány és a levegő képessége.
4 years after KFF rejected the Olympus, Britain cancelled TSR-2. And with that, the Olympus variant KFF had considered died with the program. Their caution looked prescient, but it wasn't. The decision was risk management, not prophecy. KFF had been as lucky as they'd been wise. In all, 8 prototype RM8 engines accumulated 2,600 hours on test stands before Viggen's first flight, 600 of those hours at full afterburner. By the time serial production began in 1970, total test hours had reached nearly 10,000. The engine worked, but it came with constraints. The engines had a weakness. The Swedes called it pump ningar, compressor surge. Every jet engine has a compressor map, a graph showing the relationship between airflow, pressure ratio, and engine speed. There's an operating line where the engine runs normally, and above it a surge line where the airflow breaks down. The gap between those 2 lines is called the surge margin. Lose that margin and the compressor stops, well, compressing. What happens mechanically is ugly. The high pressure air in the combustor suddenly has nowhere to go. The compressor can't push against it anymore, so the pressure reverses. Hot gas belches forward through the compressor stages, the wrong direction entirely. The engine coughs, thrust drops, and temperature spikes. The whole power plant shudders with mechanical vibration that can damage blades if it continues. At cruise altitude, you recover, reduce throttle, let the airflow re-establish and try again. At 50 meters above the trees on a low-level attack run, you had much less margin for error. The RM8A was vulnerable because the fan and compressor geometry it inherited from the JDAD was sized for a civilian engine operated in benign conditions, gentle throttle movements, steady airflow, no violent maneuvering. Military flying broke those assumptions. Rapid throttle slams disturbed inlet flow at high angles of attack, supersonic shock waves bouncing around the intake. All of these could push the compressor across the surge line. The problem would require years of refinement to fully solve. For now, it was a known weakness, documented, measured, and added to the list of things the test pilots would have to prove manageable. First serial RM8A delivery came in October 1970. Volvo Fliegmotor built 195 of them for the attack variants before switching to the redesigned RM8Bs. Laurel, who'd started as project engineer in 1962, stayed with the program, and he'd go on to manage the RM8 through its entire service life. The engine worked, but whether Sweden could afford to build the aircraft around it was about to become someone else's problem. The configuration was frozen. The wind tunnels and engineers had done what they could, but it hadn't all been smooth sailing. In 1964, 2 years before any prototype existed, the entire Viggen program had nearly died on the floor of the Swedish parliament. Ingemar Stahl was a young Chancery Secretary in a defense ministry, and he had numbers that made the Air Force nervous. He published an attack in the Social Democratic journal Tiden, arguing that Viggen would cost 30 billion krona and arrive obsolete. A Swedish skybolt business, he called it, invoking the failed British-American missile project. The program he wrote was a cuckoo in the defense nest, a single project so expensive it would starve the Army and Navy of funds they desperately needed. The accusation stung because it wasn't entirely wrong. Unit costs had been climbing since the first estimates. The Air Force had wanted 800 aircraft, and the Treasury wanted to know how Sweden would pay for them. Stahl wasn't alone. The criticism came from multiple directions. Army experts argued behind closed doors that ground-based missiles could handle coastal defense more cheaply than manned aircraft. The workforce had grown since the 1962 go-ahead, with Saab needing 500 new skilled workers every year to keep the program running. Management warned the government that 1,000 of them would be made redundant if production wasn't approved, a threat that concentrated the minds in Stockholm. In March 1964, the government appointed the Flygmaterielberedningen, a defense material commission, to investigate whether the whole program should be abandoned. The commission's brief was stark, determined whether Sweden should cancel Viggen and buy American F-4 Phantoms instead. For 18 months, the program's existence hung on a political decision that had nothing to do with aerodynamics. Volvo Flygmotor was deep into RM8 engine development. Billions of krona were already committed. None of that mattered if Parliament said no. One military expert had quietly submitted a memorandum to the Commission's chairman behind the backs of other committee members, proposing that ground forces should be prioritised at aviation's expense. In the margins, the chairman himself had written a question that could have killed the program. No development and production of J837? Questioning what would happen if they cancelled Viggen. The J37 was the planned interceptor variant. Without it, the unit aircraft concept collapsed, and Sweden would need to build a separate fighter after all. The Commission reported in 1965. Their conclusion: abandonment was impractical. The progress that Saab had made, they wrote, represented outstanding technical success. Cancelling now would waste everything already spent and leave Sweden dependent on American export approvals for its air defense. The Commission also settled another question: the government's decision to make Saab the sole supplier, responsible for total system integration, had infuriated the independent electronics industry. They called it the Tullinge bloodbath. From that point on, Saab wasn't just building an aircraft, it was running a monopoly, and everyone in Stockholm knew it. But the debate didn't end with the Commission's verdict. Years later, filmmakers would produce a documentary, funded by the government no less, calculating how many childcare centres and pensions could have been paid for instead. The vulgar debate, as one observer called it, would follow Viggen around for years. The original plan had called for 800 aircraft. The Commission cut that number sharply. The final production run would reach just 329. The Hedgehog would be built, but with far fewer quills than anyone had planned for. One parliamentary critic summed up the whole situation with a sharp analogy. The military wants a Mercedes, but we can only afford a Beetle. The numbers themselves were fairly impressive. The program's total development cost had grown from the original 8.9 billion krona in 1963 to 12 billion by 1965. Per unit costs had doubled from 10 million to 20. The frantic weight hunt, the wing spar reinforcements, the complex computer integration, every fix added costs. The Mercedes just kept getting more expensive. Saab CEO Tryggve Holm stayed defiant. After the resolution authorizing development to continue, he told the press that they'd won the first round. The victory was bittersweet. the government simultaneously postponed production by 18 months and reduced the number of aircraft on order. His view was simple: survival was victory. On the 5th of April 1965, Saab presented a full-scale mock-up to the media. The Swedish Air Force Commander-in-Chief used the occasion to name the aircraft Viggen, a variation of Askvig, the Thunderbolt, the sound heard when the Norse god Thor smashed his hammer across the sky. Though Vig is also Swedish for tough duck, fitting perhaps for an aircraft whose Canard foreplanes were named Duckwings. And so the program survived, had a name. All it needed now was an aircraft. On the 24th of November 1966, prototype 37-1 rolled out of Saab's workshop at Linköping. It didn't look like the aircraft that would eventually reach the squadrons. The dorsal spine was straight. That distinctive hump that would solve Viggen's transonic pitch problems hadn't yet been added. The Canard still had 10 degrees of dihedral, angled upwards in a V-shape. Engineers would strip it off during the final 3 months of ground testing. The aircraft that flew wouldn't be quite the same as the one they rolled out. But inside 37-1 was a flying laboratory, over 700 sensors embedded throughout the airframe. An onboard computer recorded 250 parameters simultaneously, multiple times per second. Control inputs, pressure changes, structural vibrations, all recorded for engineers to analyze later. Saab had kept the rollout private, no press, just company personnel and Air Force officials watching. Engine ground tests began immediately. A month of systems verification followed. On the 31st of January 1967, Erik Dahlström, Saab's chief test pilot, climbed into the silver aircraft for the first taxi trials that involved rolling down the runway, lifting the nose in brief hops to check the gear and control responses. Everything worked, everything was on schedule. By early February, the prototype was ready, just in time for another political crisis. Social Democratic budget proposals threatened to cut 600 million kroner from defense spending. The Air Force warned that if the cuts went through, Viggen production might have to be delayed indefinitely, not cancelled outright, but bled slowly until the program lost momentum and died of neglect. So the first flight wasn't just to be a technical milestone, it was also political ammunition. Success would prove the doubters wrong, but failure would also hand them a victory. Prototype 37-1 sat on the ramp at Malmslätt, and Erik Dahlström would be the man who would take her for her maiden flight. He'd flown some of the first flights of Tanan, Lansen and Draken. His colleagues called him Safe Dalmas, a nod to his home province of Dalarna and his reputation as a steady, reliable pair of hands. If anyone was going to prove the Canard worked, it was him. And unlike me, he was not given to dramatics, which was probably why they had chosen him. Inside the design office, the mood had a name: designer's uncertainty. Years of calculations, thousands of hours of testing, and nobody could guarantee that a Canard Delta would behave as the wind tunnels predicted. The engineers had done what they could on paper, now someone had to sit in it. The morning of the 8th of February 1967 was cold and clear, frost on the ground, blue sky above. The runway at Malmslätt white with snow, beautiful Swedish winter conditions. Saab had kept the flight private. No press, just company personnel and selected observers. If something went wrong, they didn't want cameras recording it. At 10:57 a.m., Dahlström spooled the RM-8 to full power, released the brakes and began the takeoff run. Stick back, the Canard bit into the cold air. The main delta generated lift exactly as the wind tunnel had predicted. The main gear lifted from the runway. Viggen was flying. For 43 minutes, Dahlström kept it conservative. No supersonic flight, nothing aggressive. Just proved the aircraft could fly and land safely. What surprised him was how it handled. Despite the chubby fuselage, a consequence of that oversized engine, the aircraft felt balanced. When he moved the stick, the flight path marker on his head-up display went where he pointed it and stopped when he stopped. The attitude clutch fixes Saab engineers had developed on Lansen testbeds did what they were supposed to do. That was enough for one day. He brought the aircraft down, letting it settle onto the runway and roll into a stop. Dahlstrom didn't test the clamshell doors. That system wasn't ready. Serious flight testing of the reverser wouldn't begin until 1969. After the maiden flight, his assessment was encouraging. As easily flown as a sports aircraft, far easier than Draken. That evening, there was a big party. They had much to celebrate. Over a decade of studies, hundreds of rejected configurations, billions of krona, one shape that many had said shouldn't have worked. The designer's uncertainty had lasted 5 years, and it ended in just 43 minutes. 7 prototypes would follow, years of testing, thousands of flights. Men would die proving this aircraft could do what Sweden needed it to do. But on that cold winter morning in February 1967, none of that had happened yet. Viggen was flying. This has been an incredibly interesting story to research. It's incredible to me just how much went into getting her airborne. 9 years of rejected designs, billions of krona, and a parliament that nearly killed the program twice before the first prototype ever left the ground. And we haven't even gotten to the hard part yet. Part 2 is where Viggen has to prove herself. The testing that cost lives, the production crises, the wings that started breaking, and the Cold War operations that showed whether Sweden's gamble actually worked. The JA-37, a completely different aircraft, new engine, built for high altitude interception instead of low level attack. You got the reconnaissance variants, the squadrons, the interceptions. 21 years where Viggen had to prove you didn't need to be NATO or Warsaw Pact to defend your own airspace. That's coming soon. If you haven't already, please subscribe and hit the bell notification thing down below so you don't miss it. But I wanted to say something about this aircraft. If you ever get the chance to stand in front of a Viggen, please take a moment to appreciate that you're looking at something that shouldn't have existed. A small nation with limited resources building something that matched anything in NATO and doing it independently. That tells you something about engineering and determination and about what happens when you're backed into a corner and you decide to build your way out. They could have cancelled Viggen numerous times and bought American. Our TSR-2 was cancelled because politicians said we couldn't afford it, although they could have afforded it if they had decided it mattered. Viggen existed because Sweden couldn't afford not to. That's the difference. Anyway, I'll leave that for the TSR-2 videos. So thank you once again for watching. These long-form videos take a huge amount of work, and the fact that you've stuck with me up to this point, to the end of this video, means the world to me. So until part 2, see you then. Now it's time for tea and biscuits.